All right, welcome back for part 3 of Newton's method. All right, so here's our example. Here's our problem that we have to do. We are given this. We're asked to use Newton's method to find the 6th root of 2 correct to 8 decimal places. All right, so this would be the first example where we are going to do something, and then we will decide when to stop. Because our previous example, they told us to stop at the 3rd iteration, that x sub 3. So we are going to just do this until we get 8 decimal places of accuracy. So this means right here, we're going to keep going until the first 8 decimals match. So until the first 8 decimals match. Okay, I can do that. All right, but I got a problem. Newton's method is a technique for finding when a function crosses the x-axis or when a function is equal to 0. I don't see a function in here anywhere that I'm going to set equal to 0. So what am I going to do? Well, what I'm going to do is I'm going to take what they've asked me to find and rewrite that as a function. If my job is to find a value x that is equal to the 6th root of 2, that's the same thing as saying, when will x to the 6 minus 2 be equal to 0? Raise both sides to the 6th power, move the 2 over, and now I have a function, f of x, that I can set equal to 0. Okay? All right, so Newton's method. Newton's method says that x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. Okay? Which means that I need all of this information to get moving here. Well, I've got my f of x. I can use that to find f prime of x. Okay? The only thing that I'm missing is I need an initial guess for my x sub 1. Okay? And so I'm just going to say, well, I think that it's probably some number that is somewhere between 1 and 2. So I'm just going to say 1.5 and start there. Okay. All right, so bring the calculator up, because Lord knows I'm not doing this one by hand. And let's get going here. All right, so first things first, I need to get f and f prime into my y editor. So this was, let's see, x sub 1 was f, so that would be x raised to the 6th minus 2. And y sub 2 was f prime, so that's 6x raised to the 5th. Where's the 6? 6x raised to the 5th. Okay, that looks good. And then back to here, and then, oh yeah, put my initial guess, store that into x, and now I need to do this. So that's x minus y1 of x divided by y2 of x, and then store that back into x. And so then x sub 2 is 1.293895748. X sub 3, 1.17016. So right now I've got no real accuracy. x sub 4, 1.12. So now I've got accuracy to tenths place because the 1 hasn't changed there in tenths place. Ooh, now I've got accuracy to hundredths place. So x sub 5 is 1.12. X sub 6, now I got accuracy out to 3 decimal places. So x sub 6 is 1.122, but I need 8 decimal places of accuracy. Now I've got, looks like I've almost got it there. How much accuracy do I've got there at x sub 7? 1.122462 0. So how many is that? 1, 2, 3, 4, 5, 6, 7. I got 7 decimal places of accuracy out to that 0. 1, 2, 3, 4, 5, 6, 7. And if I go again, there it is. And so the 6th root of 2 accurate to 8 decimal places, 1.1224. That's 1, 2, 3, 4, 5, 6, 7, and I'll round that to a 5, 8. And there's 8 decimal places of accuracy. Now I know what you're thinking. Well, that took a while. Yeah, and the reason that it took a while is because this was garbage. It was a garbage first guess. I should have known it was going to be much closer to 1. In fact, if I had just started with 1 as my initial guess and then run this process, 4, 5, and I'm there. 6. Okay? So a good initial guess is going to get you to your answer faster. If I had started with 1.2 as my initial guess. We'll look at that. We're already at 3 decimal places of accuracy. And there we are. Okay? So knowing a little bit about mathematics and being able to get a good initial guess is going to get you to your answer faster. But even if you give a really garbage initial guess, you can get to the right answer sooner or later. There's only about one situation where you can really screw up. Okay? Suppose that you had a function that wiggled a lot, and you were looking for this 0, but your garbage first guess puts you somewhere over here. That's going to chase you to a different 0. Okay? Or if your garbage first guess was too far this way, that would chase you to a different 0. For the most part, if you have a function and you give a reasonably good first guess, it's going to get where it needs to go pretty quickly. Now I know what you're thinking. 7 times, that doesn't seem fast. 7 times doing a simple fraction for a problem that couldn't be solved any other way. This was remarkable stuff when they developed it. And we still use this and modifications of it to this day. All right. Find correct to 6 decimal places the root of the equation cosine x equals x. So when will cosine x equal x? Well, first off, that's not a function that is equal to 0, so I need to change it. I'm going to rewrite that and say that's the same as when is cosine x minus x equal to 0. And now I do have a function, f of x, that can be set equal to 0. I know that f of x is equal to cosine x minus x. And then f prime of x is equal to, let's see, what is that going to be? Negative sine x minus 1. And all I need is a good initial guess, and I can find this. So when do you think cosine x is equal to x? Well, if I just make a quick little sketch, cosine's the one that does this, right? Y equals x looks like this. So where do you think that's going to happen? Well, that's what, pi over 2? So somewhere south of pi over 2. So how about pi over 4? Seem like a reasonable first guess? Okay, so now push buttons. So first things first, I need to put f and f prime in the calculator. This was cosine x, cosine x minus x. This was negative sine x minus 1. I'm going to do pi divided by 4, store into x as my initial guess, and then I do x minus. Now, if you don't have an 84 updated and you need that y1, you can also get there by using the variables command key right there, 2 above the 9 or 3 above the 9. Over to y variables, option 1 is function. There's y1 of x divided by variables, y variables, function, y2 of x, and store that back into x. Okay? And so I get that x, whoa, I got the arrow thing going on over here. I don't want the arrow thing. I want a pen. And so I get that x sub 2 is 0.7, because that's all the accuracy we have. X sub 3 is 0.739, because that's all the accuracy we have now. X sub 4 is 0.7390851. Well, they would round differently, so no, I'm not going to call it that, but that's 6 decimal places of accuracy, and I'm done. So I found the accuracy I needed in 4 iterations, the 4th iteration. All right, so we could take a look at this next one. It's the last one in this example. We're already at 12 minutes. We can do this. All right, so let's see what the directions say. Use Newton's method to approximate correct to 6 decimal places. So there's our accuracy we're looking for. The indicated root of blah, 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 blah on the interval 1 to, oh, okay. So we're looking to find out when that equation has a solution, but only on the interval 1 to 2, which means we need to make sure that our initial guess is something that's going to drive us towards that root that's on that interval 1 to 2. All right, so using the same logic I've been using so far, here is my function that is going to be set equal to 0. So my function f of x is the function x to the 4th minus 2x cubed plus 5x squared minus 6. The derivative of that function is 4x cubed minus 6x squared plus 10x, and just because I'm that lazy, I'm just going to simply say x of 1 is 1.5. Smack dab right in the middle of the interval. Now, it's time to push some buttons. Okay. First things first, I need to put the function and its derivative into the y editor. So my function is x raised to the 4th minus 2x raised to the 3rd plus 5x raised to the 2nd minus 6. My derivative is 4x raised to the 3rd minus 6x raised to the 2nd plus 10x. My initial guess is going to be 1.5, so I'll store that 1.5 into x. And then I'm just going to go back up and grab that command, enter. So then my x sub 2 will be 1.2625. My x sub 3 will be 1.2188077774. So it looks like we've got 1 decimal place of accuracy at this point. My x sub 4 will be 1.217563128. So now we're looking at 2 decimal places of accuracy, more or less. My x sub 5, 1.217562155. So what are we looking at now? We got the 2, we got the 1, we got the 7, we got the 5, we got the 6. So that's 1, 2, 3, 4, 5 decimal places of accuracy. We needed 6, so we got to keep going. X sub 6, 1.217562155, and it looks like we got a complete match. Oops. Complete match all the way out. So my final answer is that x should be 1.12345 6 decimal places of accuracy. There is the root to the equation x to the 4th minus 2x cubed plus 5x squared minus 6 is equal to 0 on the interval 1 to 2 using Newton's method as an approximation technique. All right, I hope you've enjoyed section 3.8 as much as I have. This brings our unit to an end, which means we have an exam covering 3.5 through 3.8 coming up. All right, take care.